Section 2.2, broadening our understanding of work. So energy can be transferred to and from system by work. Let's take a look at this diagram. So we have a system in a closed tank. So paddle wheel is connected to the system. So here's a motor, and motor rotate the paddle wheel. So it provide work to the system. So the gas in the tank is stirred. So energy is transferred to the gas by work. We have another system containing a battery. So when the battery is discharged electrically, so current flow through the batteries. So energy is transferred out of the battery by work. So it has a different form of work, mechanical work and the electric work. So in this case, energy is transferred to the gas. So work is negative in this case. This case, the battery is discharged. So in this case, battery is discharged. So work is done by the system. Sign convention of work. So since engineering thermodynamics is often concerned with internal combustion engine, turbines, and electric generators, whose purpose is to do work, it is convenient to regard work done by a system as positive. So work done by a system positive, work done on the system is negative. So consider this piston cylinder system. So work done by the system is positive. So when the gas expands, it pushes the piston. Volume increases. So pressure by the gas push the piston. Then work done by the system. So W is positive. So we have a system. Work is done by the system. W is positive. Outside is surrounding. Second case, we have a system here, and the piston is pushed. The volume decreases, pressure increases. In this case, work done on the system. Work is done on the system, and W is negative. Outside is surroundings. So this is the sign convention we will be using in this class. The energy transfer is often expressed as time rate form. So the rate of energy transfer by work is called power. Rate of energy transfer by work. So we use the symbol W dot. F is force times V, velocity. So work is force times distance, but this is the rate form. So rate form, distance x divided by time. So this is velocity. The unit of power is joule per second or watt. And in English unit, BTU per hour or feet pound force per second or horsepower. And this is the conversion between English unit and SI unit. And the first law of thermodynamics can be also expressed as the rate form. This will be discussed later. So here is a system boundaries containing gas or liquid. So pressure by the gas push the piston. So piston move from position x1 to x2. So the work by a piston cylinder system is given by pressure times A. Pressure times A is force by a gas, times the distance dx. So it is called a displacement work. So the work is force normal to the piston times dx, the distance of the piston moved in the direction of the force. So W work is F force times dx, integrate from position x1 to x2. So force can be expressed by pressure times area. This is area of the piston. And the quantity A times dx. Quantity A times dx is dV, volume, differential volume. So this expression, work can be integrated from V1 to V2, P times dV. So this is one type of mechanical work, displacement work. And it is also known as a moving boundary work. And there are different types of work, such as rotational work. Like we just saw pedal work in the system, so rotational work, and also spring work. Spring is connected to a piston cylinder system. So work is transmitted by torque on a rotating shaft, and work is done on a spring to compress or stretch. Quasi-equilibrium process. So this is an idealized process such that the gas undergoes a sequence of equilibrium states during expansion or compression process. So see this diagram, PV diagram, pressure, volume. So it's a piston cylinder device. Initially, it was state 1. So this is state 1. At state 1, pressure P1, volume V1. At state 2, pressure P2, volume V2. So initially, the volume was this much, V1, and it expands. And V2 is this. Quasi means close. Quasi means close. Equilibrium. So what is equilibrium? So when it refers to thermodynamic equilibrium, or just the equilibriums, it refers to thermal equilibrium, mechanical equilibrium, and chemical equilibrium. So thermal equilibriums describe temperature within the system is constant. So let's say if 25 degrees Celsius everywhere in the system is 25 degrees Celsius. This is thermal equilibrium. There is no temperature gradient within the system. Chemical equilibrium. So the chemical composition within the system remain constant. It doesn't change with time. So if it has a CH4 and air in the system, CH4, air, everywhere the composition are the same. And there is no chemical reaction within the system. This is called chemical equilibrium. mechanical equilibrium indicates there is no pressure change in the system. So piston cylinder system, let's say there's a force pushing the piston, and it has a gas inside, and gas also have pressure, so it also push the piston upward by the pressure. So since there is no pressure change within the system, F is equal to P, pressure by the gas, times area of the piston. So there is no pressure change in the system. This is called mechanical equilibrium. So when it refers to thermodynamic equilibrium, it means thermal equilibrium, mechanical equilibrium, and chemical equilibrium. So going back to the PV diagram, so quasi-equilibrium process describe the system remain close to an equilibrium during a process, and it is an idealized process. So let's consider a process from state 1 to state 2. So initially the system is at state 1. So assume that the heat is transferred to the system. So it caused the gas in the system to expand. And the expansion of the piston caused the property changes in the system, such as pressure, volume, and temperature. Finally, the system reaches at state 2. And it goes through a number of intermediate states. Pressure, volumes, this is state 1, state 2. So imagine it is an extremely slow process. So it goes through a number of intermediate process. And at every intermediate state, it reaches an equilibrium state. So at any intermediate state, it reaches at equilibrium. So we can define the path between the states. So why do we need the quasi-equilibrium concept? It is easy to analyze the system with the idealization. So work was defined as pressure times dV, volume 1 with 2. Integration of pressure times infinite thermal change of volume. So the work done by the gas is the area under the PV curve from point 1 to point 2. So under the area, this red part is the work, corresponds to work. So in the following examples, we will see how the process affect the work. This is an example in our textbook. Gas in a piston cylinder assembly undergoes an expansion process for which the relationship between pressure and volume is given by pressure times volume to the nth is constant. So we saw these relations in previous class. This is called polytropic process. So initially the pressure 3 bar, volume 0.1 cubic meter, and the final volume 0.2 cubic meter. Determine the work for the process. So pressure at state 2 is not given, and exponent n is 1.5, 1.0, and 0. 3 different cases. So at 3 different cases, we can also determine pressure at state 2. So state 1 is the initial condition, initial state, and state 2 is the final state. So what is known? A gas in a piston cylinder assembly undergoes a polytropic process. And evaluate the work at 3 different exponent n. Schematic and given data. So we draw the schematic piston cylinder assembly. So gas in the cylinder, but we don't know which gas it is, and actually we don't need to know what gas it is. Initial pressure and volume is given, and V2 final volume is also given. So we plot a PV curve. So P1 3 bar and V1 0.1 cubic meter, and at state 2 volume is 0.2 cubic meter, and pressure at state 2 are unknown. So the system is a closed system. The moving boundary is the only work done, only work mode, and expansion is a polytropic process. So we will determine the work at three different exponents. So work from the this is a moving boundary work. So work is pressure times difference of volume. So integrated from initial volume V1 to final volume V2. Pressure, using the polytropic process, we can express pressure in terms of volume. And integrated from V1 to V2, we got these relations. P2 V2 minus P1 V1 over 1 minus 1. So when the exponent is 1, so we have case C, exponent is case B, exponent is 1. So we cannot use this when the exponent is 1. But the other two cases, we use this expression to calculate the work. So first, when n is equal to 1.5, so we can determine the only unknown is the pressure at state 2. So we solve it for P2 when n is 1.5, P2 is 1.06 bar. So work can be calculated. So this is when n is 1.5. When the exponent n is 1, we are still using the same expression, P dV, and P PV is constant. So P is constant divided by V. So we can write constant V1 over V2, 1 over V dV, which is here. So integrations of 1 over V is a natural log. So we got this. So constant is pressure times volume, P1 V1, or P2 V2. Since P2 is unknown, we are using P1 V1. So we calculated work when n is equal to 1. For n is 0, so P times V to the 0. This is P, which is constant. So pressure remain constant, 3 bar, and volume is 0.2 cubic meter. So we still use the same expressions, W, V1, V2, P, dV, and pressure is not function of volume. So we can take P, pressure, out of the integration. So pressure times V2 minus V1. So work is 30 kilojoule when n is equal to 0. So we compare the work in 3 different cases. So N is 0, 30 kilojoule, N is 1, 20.79 kilojoule, N is 1.5, 17.6. So the processes can be plotted in PV diagram. So the process, the work during the process 1 to 2C or W1 to C, work during process 1 to B or work 1 to B, or the work during process 1 to A or 1 W1 to A. So we compare the area under the curve. So we expect 1 to C is the largest, 1 to A is the smallest. So this work is 30 kilojoule and this work is 20.79 kilojoule and this work is 17.6 kilojoule. So the area under the process corresponds to the work done by the gas. As we expected, work during the process 1 to C is the largest. Let me define W1. So what is W1? So it is the work at state 1. So does it make sense to you? So we don't define the work in a state. So work is not a property. So we cannot define work at a state. Work can be defined between 2 states. So in these questions, the area under the curve represents the work and it is dependent on the path between the states. Section 2.3, broadening our understanding of energy. So I'm going to introduce the concept of internal energy. It is the sum of all the microscopic forms of energy. So take a look at the system at the molecular level. So molecules have kinetic energies and potential energies, and trillions of molecules are bouncing around randomly in all directions. So the electrons also rotate about the nucleus, and internal energy also includes the chemical energy of molecules and nuclear energy with the nucleus of the atom itself. Internal energy, the unit of internal energy is kilojoule, or this is an extensive property. So in intensive property, we use a smaller case u. So the unit is kilojoule per kilogram, and using the molar basis, u with a bar, kilojoule per kilomole. The internal energy of a fluid depends on its temperature. So it is a property of the fluid. Go to the end of the textbook, you will find thermodynamic tables of different materials with various properties, including the internal energy. So just like the velocity and height of a system, the internal energy also needs the reference point or datum to quantify the value. There is no known absolute internal energy. So the internal energy is set to 0 at an arbitrary state. So that is why we see negative internal energy in some states. But we are only interested in the change in the internal energy using the data in the thermodynamic tables. The change in energy of a system, change in energy of a system is the kinetic energy change plus potential energy change plus internal energy change. So energy E2 minus E1. So energy transfer to or from the system equals U2 minus U1 to state 2, state 1. KE kinetic energy at state 2 minus KE1 potential energy at state 2 minus potential energy at state 1. So you need to know that we are interested in the change in the energy of a system between the states. So especially the internal energy, kinetic energy, potential energies are measured relative to the reference frame or reference point. So we are interested in the change between the states. So today we talked about the energy transfer in the form of work. So next class we will learn energy transfer by heat.